In class 1, if you remember, we studied about these two, the distributions of x bar and sum of xi, x1, x2, xn. They are random variables and all have mean mu and variance sigma square. We are not specifying the distribution of the population. That's why I have written star. Here it will be automatically normal. This will also be automatically normal. We don't need the distribution of x1, x2, xn. What we need to know is they should be IID, independent and identically distributed. At the same time, their mean and variances, they must be same. They are identical and independent, and identically distributed means their means and variances will be same. So mu of x1 and mu of x2, they are the same here. Similarly, sigma square. In this case, this one will happen. We can use the result directly, and you must have solved some problems. I'll send you some more problems you can do. Now, we'll try to use directly in today's class. That means if x follows binomial NP, x will follow. If x follows binomial, then x will be approximately distributed. We write this way. Most of the time, we don't write these dots. That's fine. But then, if you want to write x is approximately distributed, normal, NP, that is mean, NPQ. So this way we write. If x follows Poisson lambda, then x will be approximately distributed as n. Here you can write lambda lambda, mean variance. If you remember, E of x is lambda and variance of x is also lambda. In this case, E of x is NP if x follows binomial. E of x is NP, that I have written here, and variance of x is NPQ.
Sir,
We'll prove this. We'll prove this. If you want, you can write other distributions as well. But yeah, these are the ones we use frequently. So for all distribution, whatever distribution you know, if you write here, just write mean here, variance here. Normal NP, NPQ. We'll try to prove this one. Now, suppose we have this population. This is the population. And like you said, I'll take random variables. Now, x1, let me write x follows binomial NP. If x follows binomial NP, then what will happen is I will prove that x will follow normal NP, NPQ. Okay?
okay.
All right. Now, if you add Bernoulli distribution, okay? So, what I will do is to prove this one, I will start with Bernoulli distribution. I will take this way. Suppose x1 is from Bernoulli. You know Bernoulli distribution?
Yes, sir.
x1 from Bernoulli P, x2 from Bernoulli distribution, and xn from Bernoulli distribution. If I find the sum of all these, that is x1 plus x2 plus xn, then what will happen? I will get a binomial distribution. X will follow binomial NP. We write this way, 1p. binomial p or 1p you can write, they're the same. 1p, 1p, I mean not 1p, why, I mean in that case it will be binomial, just write p here. So let me write, this is Bernoulli p, this is Bernoulli p, this is Bernoulli p, and this will be binomial np. Okay,
Okay.
we know this already. Do you know this?
Sum of the sum.
Yeah, that means you toss a coin today, you toss a coin tomorrow, you toss a coin each day.
Yes,
After 30 days, you would have tossed a coin how many times?
30.
Yeah. So out of 30 times, sometimes you got a head, sometimes you got a tail, right?
Yes, sir.
So how many heads you must have got? What is the probability that you got? You got 20 heads in 30 days. Suppose out of 30 days, all days you will not get success, right?
Yes, sir.
Someday success you define. What is success? That is up to you. I'm not going to that. What I'm saying is, what is the probability that you will get 20 success? What is the probability that you will get 20 success? That will be a binomial distribution, right? What I'm saying is, individual it's a Bernoulli distribution. X follows, x1 follows Bernoulli p, let me write. x2 follows Bernoulli p, and xn follows Bernoulli p. Then I want to add all this. So if I write summation of xi, that will follow binomial np. If you want, you can write this as x or x. So if you write x is equal to summation xi, that will follow binomial np. This we know already. This is not a new one. Now using central limit theorem, let me use central limit theorem. If I use central limit theorem, I will get the distribution of summation xi. So let me write this way. Using CLT, central limit theorem, summation xi should follow normal n mu n sigma square. Now sum xi will follow normal, n is n here, approximately distributed, we have to write. What is mu here? So let me write mean is equal to p and variance is equal to pq. Similarly for x2, I will write mean is p, variance is pq. I am considering Bernoulli, not binomial. For xn also similar values will get. So let me write mu p here and sigma square pq. So if you see here, I got np and pq. By virtue of result 1 and 2, 1 is something we knew before, and using central limit theorem we got the distribution of x. Now if you compare 1 and 2, you see that binomial np is approximately distributed as normal np and pq. Similarly, you can prove the other results. Got
Sir,
it? Yeah.
I think wait, sir.
You got it?
No, sir.
So what is the problem?
Sir, X is the parent distribution, no, sir. That you're approximating using central limit theorem. That first in the last class we did the sample. What are the samples taken? X bar that we have no, approximated normal. Like that we are now for
See,
popular.
I used part 2 of the theorem.
Sir, my doubt is now we are for approximating normal distribution for the population. X
No,
is
no,
the
it's not sample and population. What I'm saying is, if you use part 2 of the central limit theorem, if x1, x2, xn follow any distribution, we have taken Bernoulli here, if x1, x2, xn follow any distribution, if you add those, that will follow a normal distribution. This is what we did last time in part 2, n mu n sigma square. I use this one.
yes, sir.
And in mu I used p, that's all. That means I took binomial distributions, Bernoulli distributions. Last time what we did is, if these are star distribution, we did this one. If this follows star distribution, this follows star distribution,
Yes,
this
sir.
follows star distribution, then this will follow n mu n sigma square. And here also we have written mu and sigma square are the mean and variance. This we studied in class 1.
Yes,
Now
sir.
this we studied already. Now in place of mu, I have taken p in today's class, and in place of sigma square pq I have taken, and in place of star distribution I have taken Bernoulli. And so this is a particular case of what we studied last time. Suppose x follows any distribution, I will write exponential, x follows exponential 0.4. What is the probability that x is greater than 2? I want to find this one. We can find directly. Let me find directly here. You know how to find directly? This is using CLT, and this one directly. Okay, this one will do directly. How to do this problem directly? Probability x greater than 2. We can integrate from 2 to infinity, right?
Yes, sir. 2 to infinity.
Yeah.
Lambda e
Yes.
power minus lambda x.
So we'll write exponential distribution formula. F of x will be lambda e minus lambda x. F of x will be lambda e power minus lambda x, and this will be from 0 to infinity. This is the formula, and lambda is given 0.4 here. Okay. Now instead of integrating, we have another way also. We can write this as
Minus e power minus lambda x.
1 minus, there is a formula for this one, that is f of 2. There is a formula for this one, 1 minus e power minus lambda x. This is the formula. This is the formula. So finally you get e power minus lambda x, and x is 2 here, and lambda is 0.4 here. Even I can directly use the formula. There is a formula for this one. Instead of doing all this, directly we can use the formula. Probability x greater than x, that will be equal to e minus lambda x. We'll use this formula. E minus lambda is 0.4 and x is 2 here. That means e power minus 0.8. See the calculator and tell me this value.
0.449.
Okay, 0.449. There is a good probability. If x follows exponential 0.4, there is a probability that x greater than 2, it's around, less than 50%. Now we'll use CLT. Using CLT, if x follows exponential lambda, if you use CLT, exponential lambda will be approximately distributed as normal 1 upon lambda, 1 upon lambda. So how you can remember? You just write the mean here and variance here.
Okay.
Yeah, exponential lambda will follow normal 1 by lambda, 1 by lambda. 1 by lambda, 1 by lambda square. Variance is 1 by lambda square.
I see.
Yeah, now I want to find probability that x is greater than 2. Then that will be equal to probability that x distribution I know. So let me write here normal 1 upon lambda is 4. What is 1 upon lambda square?
Huh?
What is 1 upon lambda square? Let me write this way only, 0.16. Is it okay?
Yes, sir.
Now, probability x greater than 2 I want. I will change it to standard normal. Then it will be probability x minus 4 divided by square root of this one.
Yes, sir.
That will be 0.4, right?
Point. Sir,
Yeah, 1 upon 0.4.
okay, okay, sir.
2 minus 4 divided by 1 upon 0.4. And this will be standard normal, and that will be greater than minus 2 divided by 4 by 10. So that will be minus 0.5. Is it okay?
Yes, sir.
So you know what is that greater than minus 0.5? That means what? That means this one we want. Here we have minus 0.5. We want this area. We want to the right, but from the table we will get from the left. So what I want to say here is this area you will not get from the actuarial table directly, because
Yes.
this is 0 here. So this area is already 0.5, this is half and this side half. So this area is 0.5, and see, this one will be equal to this one. This is minus 0.5, you write plus 0.5 here, and this side area you find they will be equal. You can leave this much and this much, they are symmetrical, they are equal. So greater than this one and less than this one, they are equal. So we have to see from the actual table for 0.5. 0.69. Now this is a problem where I've just found and I verified they are not matching. That's fine, because there are a whole lot of conditions. Okay. And particularly when we talk about exponential gamma distribution, there is still a problem. It's not that approximately. It's not that approximate. Okay. However, if you take other distributions, they will be more approximate. With 10 tosses of a fair coin, what are the chances of 5 heads? Okay. Chances of 5 heads. That means we want to find probability that you will get 5 heads here. Probability that you will get 5 heads. We know probability x is equal to x because x follows binomial distribution with n10, binomial distribution n10 and probability half. It's not given, and it's a fair coin. That means I can take half here, and then I know n, I know p. N is 10 here, p is half here. So I can write the formula nx px q power n minus x.
Yes, sir.
And then it will be probability x is equal to x, 10, 5,
Right.
p power, p is half, will replace by half, p power 5, q power 5. So that will be 10, 5, p is half here, q is also half here. So you can add these two, you will get 10 here. 10 factorial divided by 5 factorial, 5 factorial, and 1 divided by 2 power 10. You find this value.
Zero point 246.
Okay, 0.246. Now see, there is a problem. See, it's like this. Can you approximate a discrete distribution with a continuous distribution? Can you approximate a discrete distribution with a continuous distribution? That is the question. That means what I want to say is, when I talk about a discrete distribution, you have probability like this. when you talk about a discrete distribution, you have always discrete probabilities like this. This is one probability, this is one probability, this is one probability, this is one probability. These are the probabilities. When I talk about a continuous distribution, the probabilities are like this. So when you approximate by using a normal distribution, see, we have probabilities like this continuously. We don't have any gap between these two. Okay, it's like you can't approximate a skeleton here with a human, because we have flesh, and here skeleton, you see there will be gaps here. There will be gaps here. Coming to this one, if you see, I can use central limit theorem, but there is a problem. We'll go to that. So let me, yeah, tell me.
Correction.
Yeah, continuity correction. That's what I'm saying. See, applying CLT, if you apply CLT, X follows binomial 10 half I wrote. So X will be approximately distributed as normal NP and NPQ I can write. Then X will be approximately distributed as normal. This is 5 and this will be 2.5. Now, if you see this graph, I will show this graph here. This is the normal distribution graph, and if you see, this is 5, this is mean is 5 here, and now if you see directly, this is 5 here, this is 5 here. So this is our part 1, this is our part 2. And in part 1 we found the probability that X is 5. We got this probability 0.246. This probability directly, this probability, this is the probability 0.246. This is the probability that X is 5, 0.246. Forget about the boundary. This is not important now. The probability we want, probability that this is the highest one, 0.246. Now come here. This is normal distribution. This is binomial 10.5. This is binomial 10.5 graph, and this is normal mean 5. Here also mean 5, NP, 10 multiplied by half, that is 5. And variance here 2.5. That means a standard deviation of 1 point something. So according to that, I drew the graph. Now suppose you want to find probability that X will be 5. If you see the white type of the line you see between these two, and here if you see, there will be no line actually. Yeah, I mean, if you want to find point-wise probability in normal, then what will happen? Now what we said is this binomial distribution we approximated using a normal distribution, which was not possible in any case. We can't bring, there is an English movie Frankenstein, so there they tried to make a skeleton a human. Okay, that's a picture, but here it's not possible. So that's a very old picture. Now coming to this one, how this distribution, when we talk about continuous distribution to continuous distribution, it's fine. When we talk about continuous to continuous distribution, what will happen? Suppose you talk about exponential distribution and it's positively skewed, then if you apply a little bit pressure here, it will become like this. What I want to say is, if you have distribution like this, this is continuous and this is also continuous. The shape is only changing. There is absolute no problem. These are the figure. You can't put water here. Okay, these are like cloth, you can say. There are no gaps. But coming to this one, this was given, and we want to use normal distribution here. So from binomial, when you use normal, we need continuity correction, because what will happen is, without using continuity correction means what? That is your interpretation. Okay, how you interpret. Once you say these two graphs are equal, here we have only value at 4, we have value at 3, we have value at 2, we have value at 6, we have value at 7, we have value at 8, we have value at 9. Whenever we talk about 5 here, you think that 5 is actually 4.5 to 5.5. 5 is actually 4.5 to 5.5. So how you count? Actually, you count discrete process this way: 1, 2, 3, 4, 5, 6, 7. This way we count normally. In continuous process, whenever you talk about 4, you think that 4 is actually 3.5 to 4.5. So this one point is equivalent to this line. This one point is equivalent to this line. Similarly, this 1.3, suppose this line, and this 1.2, this line, 1.5 to 2.5. That way what will happen? You will cover the whole area. See, you want to cover area here, not point. What you want here is, you want to cover the whole area. The whole area is 1. If you add the lines, that should be equal to 1. There is a difference. Here we have lines, here we have area. These are the lines, these are the areas. So this probability, when you want to find 5, because there is nothing between 4 and 5, here there is everything between 4 and 5. So 5 here is equivalent to 4.5 to 5.5 here. So you see, we got this area. Similarly, 4 here will make 4.5 to 3.5. This is 3.5, this is 4.5. You add here, so you cover this area. So this probability should be equal to this probability, because there is no probability here. Similarly, 5.5 to 6.5. Suppose this is 7. So this area should be equal to this area, only this length. Okay, this probability and probability in continuous is area probability. This probability is equal to this area, this probability is equal to this area, this probability is equal to this area. If you do this way, if you interpret this way, then sum of all the areas here, that will be 1. Here sum of the probabilities, that will be 1. Got it?
Yes, sir.
Got it?
Yes, sir.
Okay. Now, suppose I will ask, what is the meaning of x is 5 in continuity correction? Because 5 says I am 4.5 to 5.5. 5 says I am 4.5 to 5.5. So x is 5. That means x is between 4.5 to 5.5. This is continuity correction. Now, if x is 6, then x will be between 5.5 to 6.5. If x greater than 6, then x will be greater than 6.5, because 6 already took up to 6.5. So greater than 6 means greater than 6.5. X less than 4, that means x will be less than 3.5, because 4 means 3.5 to 4.5. 3.5 is already taken. 3.5 to 4.5 already taken by 4. So less than 4 means less than 3.5. Similarly, if I write x less than or equal to 10, suppose, then you have to write x less than 11. Then you have to apply continuity correction, because this is discrete. Then you need to write x less than 10.5, because 11 already taken 10.5 to 11.5. So in most of the cases you will get this way. However, if you get this way, then you have to write this way, then you have to apply continuity correction. You will get this one. Okay?
Once again, sir. Okay, sir.
Now let's do this problem. So here we need to find the probability that x is equal to 5. So if you apply continuity correction, it will be probability x 4.5 to 5.5.
824.
Yeah, and then you can find this probability by standardizing. So let me write probability 4.5 minus 5 divided by square root of 2.5. And if you find these values, minus 0.32, you will get 0.32 here. And then again here, if you see this one, let me write this way, probability z is less than 0.32 minus probability z is less than minus 0.32, and that will be probability z less than 0.32 minus, here this one you can write 1 minus probability, see left hand, I will show you one graph here. See, this is what we wanted to know. This is minus 0.32, this area to the left, that is equal to the area to the right. This area and this area, they are the same, because normal distribution is symmetrical about mean standard normal distribution. So this area minus 0.32 and this area right to 0.32, that means probability that z is greater than 0.32 and probability that z is less than minus 0.32, they are the same.
Okay.
So if I had this one, then that will be probability z is, let me write here, probability z is less than 0.32 minus probability left to 0.32 is right to 0.32. This is positive, this is negative. Then the first one is same and the second one is 1 minus probability z is less than 0.32. So now you will get 2 probability z is less than 0.32 minus 1. So this way if you find, you have to see only once, okay, and you find the answer, you will get it, probability z is less than 0.32, you can see the table, and finally you will get the answer.
Okay, sir.
Yeah, that is 0.6255. I already found it. 0.6255 is the answer. This is 0.246. Is it correct? Maybe I was not correct. So what is the answer here?
0.2514, sir.
Okay, 0.2514.